Divide and conquer algorithms. Divide and conquer is a top-down technique for designing algorithms that consists of dividing the problem into smaller sub-problems, hoping that the solutions of the sub-problems are easier to find, and then composing the partial solutions into the solution of the original problem. Little more formally, divide and conquer paradigm consists of these phases: breaking the problem into several subproblems that are similar to the original problem but smaller in size, solve the subproblem recursively, successively and independently, and then combine these solutions into subproblems to create a solution to the original problem. Let us look at an example. Binary search is the simplest and an extremely well-known instance of divide and conquer paradigm. Given an ordered array of n elements, the basic idea of binary search is that for a given element, we probe the middle element of the array. We continue in either the lower or upper segment of the array, depending on the outcome of the probe, until we reach the required element. Problem statement: let A 1 to n be an array of non-decreasing sorted order, that is, A of I less than or equal to A of j, whenever 1 less than or equal to I less than or equal to j less than or equal to n. Let Q be the query point. The problem consists of finding Q in the array A. If Q is not in A, then find the position where Q might be inserted. Formally, find the index I such that 1 less than or equal to I less than or equal to n plus 1 and A of I minus 1 less than x less than or equal to A of I. The approach we can follow is a sequential approach. Sequential search. Look sequentially at each element of A until either we reach at the end of an array A or find an item no smaller than Q. So for I is equal to 1 to n, do if A of I greater than or equal to Q, then you return index I, or else you return index n plus 1. So this is the sequential search for Q in array A. This algorithm clearly takes a theta r, where r is the index returned. This is omega n in the worst case and order of 1 in the best case. If the elements of an array A are distinct and query point Q is indeed in the array, then loop is executed n plus 1 by 2 average number of times. On average, as well as the worst case, sequential search takes theta n time. Binary search. Look for Q either in the first half or in the second half of the array A. Compare Q to an element in the middle, n by 2, of the array, in the index n by 2 of the array. Let k is equal to n by 2. If q less than or equal to a of k, then search in the a1 to k part of the array. Otherwise, search t k plus 1 to n for q. Binary search for q in subarray a, I, so on till j, with the promise that a of I minus 1 less than x less than or equal to a of j. If I is equal to j, then return I, so this is the index. K is equal to I plus j by 2. If q less than or equal to a of k, then return binary search of a I minus k comma q, else return binary search of a k plus 1 so on till j comma q. Binary search can be accomplished in logarithmic time in the worst case, that is t of n is equal to theta log n. This version of the binary search takes logarithmic time in the best case. Iterative version of binary search. Interactive binary search for q in array a1 to n. If u greater than a n, then return n plus 1. If I is equal to 1, no, initialize I is equal to 1, j is equal to n, while I less than j, do, so you loop over and k will be equal to, you assign k the value I plus j by 2. If q is less than or equal to a of k, then j is equal to k, else I will be equal to k plus 1. Return I. The analysis of the iterative algorithm is the same as the recursive one.